in the ring of differential operators, there are several open problems, old open problems. So the first one is presumably the most famous, I'm not sure the most important, so-called Nakai conjecture. This is basically give a regularity criteria via differential operators. And the answer is very natural one. And another one is when the ring of differential operators on an algebraic affine variety is finitely generated algebra, it is wide open. Another problem is to give a left Noetherianity or right Noetherianity criteria. And these problems are different because the rings of differential operators, they are not left-right symmetric. And another open problem, it was open problem, is to give a simplicity criteria. And 2 years ago, I settled this problem, and this is the goal of my talk to explain. And this settled in arbitrary characteristics. So this is N for the algebras of essentially finite type in arbitrary characteristic. And surprisingly, it's also give for arbitrary commutative rings. So this is the second result. So what I'm going to do, I will introduce you to the area of differential operators in both characteristics very briefly. Then you have the feeling of the area. They are very different area, characteristic 0 and characteristic P. Characteristic P is surprisingly much more difficult area and almost opposite to characteristic 0. So I will recall the smooth case. And also I will recall the state of art in as far as simplicity criteria is concerned, actually for curves and for surfaces. And then I will explain my result. So would you please, next page. Okay, so K is an arbitrary field of arbitrary characteristic, not necessarily algebraically closed. And we denote by R is a commutative K algebra. And there R is a set of K derivations of the algebra R. Then the ring of differential operators, which is denoted clearly dr, is a union of left and right R modules. At the moment, this is just a union of vector spaces, which is given recursively in the following way. So suppose D0 is by definition, this is a left multiplication by the elements of R. So we have R. Now we look at all possible linear K linear maps from R to R. Clearly, the ring R can be represented as a left multiplication. So it sits there because we assume the ring has an identity element. So this is the D0. And then inductively, Di of R is defined as on the third line from the bottom. So it means this is all linear maps U such that the commutator with all elements from R belongs to the previous step, previous vector space, right? And this is a definition. So it's defined in this way, not explicitly, but this is a very good definition as far as if you want to do some abstract research, not for computation, not even for computation is good, but this is a nice definition. Okay, would you please, next page. So now from the very definition, this is a filtration, the algebra filtration, and this is follows from the definition because this commutator is given by derivations, right? So this is a condition on the derivation which corresponds to the commutative ring R inside the algebra of all K linear map from R to R. And from this it follows straight away just that this is algebra filtration. And also by the very definition, these spaces Di are simply left and right R modules. There is important subalgebra which is generated by R and all derivation, and this algebra is called the derivation ring. So now look at the case. So now R is arbitrary commutative. No, here we defined for algebras, but this can be done for arbitrary commutative rings. One can say even for non-commutative, but the point is for non-commutative, there are some problems, right? Which is not very good definition, because, for example, simple algebras, it's tend to everything concentrated in degree 0, so you don't expect the usual features of differential operators. But let me look at the case when algebra R is a regular affine domain. Regular global dimension is finite, and of course dimension which is not smaller than 1, and at the moment characteristic 0. So in the geometric stem, this is the coordinate ring of a smooth irreducible affine algebraic variety on X of dimension n. Next, please. So now, then the set of derivation is a finitely generated projective R module of rank n, and the ring is equal to this derivation ring. I is generated by the commutative ring itself and the derivations. And the algebra is simple Noetherian domain of Gelfand-Kirillov dimension, which is twice the dimension of the algebra R, or in the geometric stems, twice of the dimension of the variety. Then the next result, which was established in 1971 by Bernstein, in order to give an answer to the question of Gelfand, like I don't know, 20 years ago, about extension of certain integral meromorphic extension. And surprisingly, the answer to this question was given independently by, as I remember, Atiyah and Gelfand and Bernstein in analytic terms. And then Bernstein found another very short proof using pure algebra, using differential operators. And in this paper, he proved his famous Bernstein inequality, which simply says that if you take finitely generated D module, its Gelfand-Kirillov dimension cannot be smaller than n. And this is very important inequality. And this is the origin of the D modules. So the algebraic D modules actually start from this paper. And of course, it is a corollary of some facts from commutative algebra that the Gelfand-Kirillov dimension of modules can be n, n plus 1, and 2n. And when you look at the simple and modules with the minimal possible Gelfand-Kirillov dimension, which is n, are called holonomic. And this is the most important class of modules, and many open questions like the Jacobian conjecture, the Dixmé conjecture, these are the question purely about holonomic modules. There are not so many holonomic modules, and there is another result of Bernstein and Lunz, simply saying that if you choose a random simple module, it has dimension 2n minus 1, not n, so it's far from being holonomic. No, and the global dimension is equal to m. So this page explained that the rings of differential operators on smooth algebraic variety have very nice, pleasant algebraic properties. So what about characteristic P? Next page, please. So in characteristic P, situation is almost opposite, but there are kind of important intersections. So first of all, the derivation is also finitely generated projective module. In smooth case, we consider smooth case. So the algebra is regular, i.e. smooth if in this context. But then the differential operators are not generated by derivations. In fact, because partial derivatives are nilpotent, actually. No, if you compare with polynomial case, you have partial derivatives, and partial derivatives are obviously nilpotent element of the algebra, and this is the trouble. This is the reason why this theory is so different from characteristic 0. But the common feature is that the algebra is simple, and this is the only common feature between characteristic 0 and characteristic P. And the algebra of differential operators is not finitely generated, not Noetherian, not a domain, contains plenty of nilpotent elements. And moreover, its Gelfand-Kirillov dimension is n, not 2n as geometric intuition says, as it should be. And it was a long-standing problem how to define the holonomic module. And there were several attempts how to do it, because you see clearly the module should exist in characteristic P. But the point is, and the result should be somehow dimension should be n as in characteristic 0. But if your algebra has, and the answer should be twice smaller than the Gelfand-Kirill dimension of the rings of differential operators. But from the very beginning, you have the Gelfand-Kirill dimension is twice smaller. So it means, and also there are simple module of Gelfand-Kirill dimension, simple modules of Gelfand-Kirill dimension 0. So in some sense, it's, you see in characteristic 0, this is impossible. So, but then when I started to look at this problem, I find the solution, i.e. I proved the inequality of Bernstein in characteristic 0 in 2008, and I realized that the Gelfand-Kirill dimension is the wrong dimension. And as a result, I introduced a new dimension, which is I call simply capital dim, and using it, prove the inequality and analog of the inequality of Bernstein, which is simply given in this fashion, that dimension cannot be smaller than n. And now you see the difference between Noetherian and not Noetherian algebras, finitely generated algebras and not finitely generated algebras. This is new dimension. If you look at even cyclic module, non-zero can be arbitrary real number from the interval n to m. In characteristic 0, we have the Gelfand-Kirill dimension can be natural numbers from this interval, but in characteristic P, it can be any real number. Suppose we have, I don't know, e to the power pi, you will find the module with that dimension. So now comes the problem of introducing the holonomic module. So simply saying that the holonomic module is a module with Gelfand-Kirill, with this dimension dim should be empty. You see here at the last line, instead of GK dimension should be this new dimension. Yes, sorry about that. This is a not correct definition because of this result that if you take n plus arbitrary epsilon, you will find the module with these Gelfand-Kirill dimensions. So, and real numbers are not enough to distinguish all this kind of growth of all these modules, you see. So now I did introduce actually characteristic free definition of holonomic modules, and they have the same nice property as in characteristic 0. For example, any holonomic module has finite lengths, and every submodule and factor module, holonomic module, are also holonomic, and so on and so on. Next page, please. So now look at the two basic examples. If you want to start the differential operators, this is the most important example. So suppose you have a polynomial ring in n variables, and in characteristic 0, differential operators are generated by x's and the partial derivatives. And when we look in characteristic P, they are generated by infinitely many generators, and this is given by this fraction, d to the power j over j factorial. So how this should be treated? Of course, suppose characteristic 2, we cannot divide by 2 factorial. But what you have to do, you have to apply as if characteristic 0 and take the modulo P, and the result will be all right. So we have infinitely many generators, and each of these elements is nilpotent, right? And this gives you a problem. This, you see, since you have many nilpotent elements, you can adjust your growth in a way that it behaves in arbitrary, unpredictable way you want. And this is the reason why for this result that the new dimension, capital D, can be arbitrary real number from the interval n to n. Next page, please. Okay, so now simplicity criteria. So the results, first of all, the case of curves was settled by Smith and Stafford in 88 in characteristic 0, right? In characteristic P, you see this area, even nobody looked at seriously. So suppose X is an irreducible affine algebraic curve of an algebraically closed field of characteristic 0, and we denote X tilde its normalization, and pi This is a map from the normalization to X. And we look at differential operators on the variety X and its normalization. Then the following statements are equivalent. And actually, this is a simplicity criteria. This map, the normalization map, is injective. And dx is a simple ring and Morita equivalent to dx bar. So now actually the case of curves, it's a very lucky case because we know that for curves, normalization is always smooth variety. Hence the rings dx tilde is simple. The original ring dx is Morita equivalent to dx tilde, which is simple, but Morita equivalence preserves many properties, including simplicity. So it means this result, simplicity, is given for free because of this coincidence that the normalization is smooth and hence the differential operators are simple. And the third condition is the global dimension of the ring is 1. And the fourth equivalent condition is the associated graded algebra is finitely generated K algebra. And since this algebra is commutative, hence grade GUR dx is Noetherian, hence the original algebra is Noetherian. So it means in these 4 conditions, you can say that, that the global dimension is equivalent to simplicity. And some other condition like associated graded algebra is Noetherian. Okay, next slide, please. So now what about the surfaces? So here is a result Chamary and Stafford. Suppose S is an irreducible affine algebraic variety of dimension 2 over algebraically closed field of characteristic 0, and X bar is non-singular. So we assume that normalization is non-singular, i.e. as in the situation for curves, this is given for free, this is the theorem. But this is not the case for surfaces. The normalization can be singular. So then the ring is simple if and only if S2 condition, third condition 2 holds, and this map is injective. The normalization map is injective. And furthermore, in this case, the ring dx and dx bar are Morita equivalent. So it means we have the same kind of situation. So this kind of criteria is given, simplicity criteria is given for free, because if we assume that normalization is non-singular and prove that the original ring is Morita equivalent, which is not difficult result, there is explicit by module which is give this, then simplicity criteria is given for free, right? Okay, so in the last 12 minutes, I will explain my results. So would you please next page? So let me just set up to give definition in order to explain the result. So I'm going to explain the simplicity criteria for a domain of essentially finite type. Okay, so K is a field of arbitrary characteristic. Pn is a polynomial algebra. D1 and so on Dn are partial derivatives. So now we consider a prime ideal inside the polynomial ring Pn, which is not maximal. No, if you maximal, you have a field, so differential operators can be easily described in this situation. And this is a completely different story from okay, so we assume that this is geometric situation. We have a prime ideal, but it's not maximal. So we fix the generator of this ideal F1, Fm, and consider the factor algebra, which is obviously domain because we assume that ideal is prime. Then we denote by Q the field of fraction of this commutative domain, and by pi is natural epimorphism from the polynomial ring to our algebra. And we will not use bar in the definition because, yeah, it's kind of, okay. So next slide, please. So now we have M generators of our ideal F1, F2, Fm. So when we look at the Jacobian matrix, i.e. this is M times N matrix of partial derivatives of the generators, and then take this Jacobian matrix modulo prime ideal. And we can see that this matrix, which is denoted J bar, as a matrix with coefficient in the field of fractions of our algebra. And we denote by R is the rank of the Jacobian matrix over Q over the field of fraction. So now we come to the very important ideal, which is called the Jacobian ideal of the algebra. So this is by definition is generated by all R times R minus of the Jacobian matrix. And now we have a beautiful Jacobian criterion of regularity. And suppose the field is perfect. So in particular, all field of characteristics 0 are perfect. Then criteria is said that the algebra is regular if and only if the Jacobian ideal is the whole algebra. So very nice criteria, very effective way. So now we look at the R tuples. I, this is the indices of the generators of the prime ideal, capital I, and also J1, JR, this is are indices of X1 and Xn. And we look at the corresponding minor, delta Ij. So simply take R times R matrix, which is denoted by I rows and J's columns, and take the determinant, and you will have an element of A. Okay, next slide, please. So then we call this element I respectively J is non-singular if the determinant is non-zero. And we denoted I, R, and J are the set of all non-singular R tuples. Now it's easy exercise that delta Ij is non-zero if and only if I belongs to capital I and J to capital J. And a localization of an affine algebra is called an algebra of essentially finite type. So it means, and we denoted this algebra by Kelly A. So by definition, any localization of that kind is called, by definition, is an algebra of essentially finite type. And also for essentially for the algebras of essentially finite type of a perfect field, there is the same criterion of regularity. So our algebra is regular if and only if the Jacobian ideal is simply Kelly A, the whole algebra. Next slide, please. So now we come to the main result, one of two main results of my talk, and this is the simplicity criteria for the algebras of essentially finite type. So let K be an algebra, be a commutative domain of essentially finite type of a perfect field, and AR be the Jacobian ideal, then the following statements are equivalent. So the algebra of differential operators is a simple algebra. So the second condition, so when we take arbitrary power of the Jacobian ideal and generate the ideal inside the differential operators, we will get dA. And the third condition, we have this particular elements of your algebra delta Lj. This is R cross R minors of the Jacobian matrix. So arbitrary power of these elements generate the whole algebra dA. For example, if you have a smooth case, then according to the Jacobian criterion of regularity, our ideal German R is equal A, contains the identity element. So it means from this, we easily deduce that every ring, that the ring of differential operators on a smooth algebraic variety is simple straight away, because your Jacobian ideal is is generated by 1, hence arbitrary power contains 1, and we are done. So this is surprisingly very simple answer, because you see, when we look at the situation to known criteria, they use geometric terms, but here answer is given in pure algebraic terms, and as you see, so the answer couldn't be simpler. The importance of this result, you know that you have to check. So we have found the elements or the ideals inside your commutative algebra. Then if you generate a two-sided ideal, you can tell you whether the ring is simple or not. Okay, next slide, please. So now we can, so now it's a corollary, it's very easy. Suppose you have a semi-prime commutative algebra of essentially finite type, then the algebra is simple if and only if algebra is a domain. And the algebra dA is simple, hence we use the previous criteria. This is easy corollary. Okay, so the next question is, what about the situation arbitrary commutative algebra, for example, Z? For example, rings not over fields, but over, say, arbitrary commutative. So let me introduce some definitions in order to formulate the second criteria in this general situation. So an ideal A of the algebra R is called the R stable if it's stable under all derivations. So it means when we apply any derivation to the ideal, we stay inside. And the next criteria is the simplicity criteria for the algebra of differential operator over arbitrary commutative algebra. So would you please, next slide, please, here. So suppose R is a commutative algebra over arbitrary field, right? Okay, we stick here to algebras, but this result is true for without this assumption. So then, and suppose we have a non-zero ideal inside the ring of differential operators. Then when we look at intersection with the commutative algebra inside of dr, we've got obviously ideal. Then this ideal is non-zero. And this is important point. When we start with a non-zero ideal inside the differential operators, when we intersect this commutative algebra, we've got a non-zero ideal, which is stable with respect to all derivation, and such that when we produce the ideal in the algebra of differential operators, we've got the ideal I. Sorry, in this equality in the fourth line, it shouldn't be zero, right? Sorry, it shouldn't be zero. Right, okay, so this is the first statement. So from this statement, so now we have a criteria when algebra is not simple. So the algebra DI is not simple if there is a proper derivation stable ideal such that when we generate the ideal inside the rings of differential operators and then intersect it with R, we've got the original ideal. So it means and this can be used in practical terms, how decide. Suppose you find derivation stable ideal, usually there are not so many of them because commutative algebra has a huge number of derivation to find something stable. Yeah, it's not so many. And if you found that the last condition doesn't hold, right? So it means your algebra is simple. No, you have to prove that this condition, yeah, all ideas. Sorry. Okay, and finally, that condition gives you a glimpse how ideals in the rings of differential operators look like. And suppose field is perfect and our algebra is a domain of essentially finite type, and we have the Jacobian ideal, and we take arbitrary ideal inside the rings of differential operators. And suppose this ideal is non-zero, then we know that the intersection with the original algebra is non-zero, i.e. with commutative algebra is non-zero, and this ideal contains the power of the Jacobian ideal. So it means we know more or less how the ideals look like. Okay, so thank you very much for your attention.